Alrighty. This is a good lecture. It's a little mathy, but it is essentially everything you need to know about energy, what energy is, and how energy changes. So now we're getting into the interesting parts of this course, in my opinion. Alright, so first off, though, let us review what we talked about in the previous lecture, which was the dot product. The dot product, remember, was the definition of the dot product of two vectors. I take vector A, I dot it with vector B. It's a way for me to multiply two vectors together, and I get out a scalar. I get out a single number. It has nothing to do with direction. Two vectors come in, one number comes out. And we saw in the previous lecture there were two different ways I could write down what the dot product is. One way, the computational way, is to take all the x-coordinates, multiply them together, add that to the y-coordinates after I multiply them together. If there was 3D, that would be plus the z components after I multiply them together. At the end of the class, we proved that there's a geometric interpretation of the dot product, where it is the product of the two magnitudes multiplied by the cosine of the angle between the two vectors. I guess it should be pointed out, this angle is always less than or equal to 180 degrees. So if you ever have two vectors like this, and you're wondering, do I measure this angle or do I measure this angle? It is always the smaller of the two, as the smaller of the angles that you can draw. So theta is always less than 180 degrees. The geometric interpretation is that this is giving us a projection of one vector on another. Actually, I'll change the symbol so it matches the equation it's right next to. A way to interpret the dot product is that if I have two vectors, A and B, their dot product is telling me about how much one of the vectors is pointing in the same direction as the other. So in this case, the way I've drawn it, I have vectors A and B, black and green. I can draw a little dotted line down to show that there is a part of A that points in the same direction as B. And I could maybe call that component A parallel to B. Geometrically, that is just a cosine theta for whatever the angle is between those two vectors. But notice in the geometric interpretation, that appears as part of the dot product. And then you are multiplying as well by the length of the other vector, in this case B. And then we also show that there are various properties that the dot product obeys, many of them akin to the product rules or the multiplication rules we know from algebra and calculus. It is commutative. There is a product rule for the derivative. Scalars can fly around and it doesn't matter which vector they're attached to. And particularly one that is useful to remember is that a vector dotted with itself is just the magnitude squared. We showed that using the computational version last lecture, but you can also see it by the geometric version. A dot A is the magnitude of A times the magnitude of A times the cosine of the angle between them. But it's the same vector. There is no angle between them. And the cosine of 0 is just 1. That is indeed the magnitude squared. Suppose you had vectors A and B, you took their dot product, and it equaled 0. What does that imply? Well, A dot B is, by the geometric version, the magnitudes multiplied by the angle between them. Magnitudes are never negative, and they're only 0 if the vector is 0. And really, if we're talking about the dot product with the 0th vector, that's kind of nonsense. So this is always greater than 0, this is greater than 0. So the only way for this entire thing to be 0 is if cosine of theta equals 0, which implies that theta is pi over 2. which implies that theta is 90 degrees, which implies that A and B are perpendicular to one another. So if I ever give you two vectors and their dot product is 0, you can immediately say they are perpendicular to one another. There's nothing else you need to do or show. You know that if their dot product is 0, they are perpendicular. Let's look at the geometric interpretation a little bit more. Suppose I have a coordinate system, and I have some vector here that is 3, 3. I'll call it r. And I want to know what angle it makes with the x-axis. We have already done this problem, or problems like this. You can throw down and identify the triangle. This has length 3, because the first coordinate is 3. You go over 3, and then you go up 3. Geometrically, it is very straightforward to find what this angle is. You know, I could use tangent. I could say tangent of theta is SOHCAHTOA, opposite over adjacent, equals 1. But theta is only equal to 1 if theta is 45 degrees. I could have also, say, calculated the magnitude of this vector. It would have been 3 squared plus 3 squared. That is the same thing as the square root of 2 times 3 squared. That is the same thing as the square root of 2 times 3. And then I could have said maybe cosine of theta is SOHCAHTOA adjacent over hypotenuse. That is the same thing as 1 over the square root of 2. If I rationalize the denominator, that's the same thing as square root of 2 over 2. That's one of the few you might have had to memorize. Theta is 45 degrees. Now, can we think of this in terms of the dot product? For the dot product, I need two vectors. But recall when we talked about unit vectors, we have vectors that represent the direction of the horizontal motion and the direction of the vertical motion, the IJK notation. So I can write this unit, or this axis here. So there's r again, 3, 3. But instead of a coordinate system, let me get rid of that. I can also just think of this as a vector I, which is 1, 0. That was just a vector that represented what was going on in the horizontal direction. And again, I could ask, what is this angle between them? In that case, I could do r dot I. That is just 3 times 1 plus 3 times 0. That is just 3. R dot I also is the magnitude of r times the magnitude of I times the cosine of the angle between the two. We calculated the magnitude of r above. That was this. The magnitude of I is just 1 times cosine of theta. So combining these two, since they're both equal to the dot product, that says that 3 equals 2, whoops, have I been writing this wrong? No. Root 2 times 3 times cosine of theta. Or cosine of theta is again 1 over root 2. Same as what we had before. So again, theta is 45 degrees. That's how you could find the angle between two vectors. Give me two vectors. I'll take their dot product. I'll get a number by the computational version. I can also take their magnitudes and set that equal to the product of their magnitudes times cosine of theta. And then I could solve for theta, perhaps. This is super helpful when when both vectors rather are not the nice axes. So suppose I have one vector r, which is 1, 3, and then I have another vector s, which maybe it's 2, 2. And I could ask, what is the angle between these two vectors? Here, theta is not measured from either axis. Now again, I could still do this geometrically. I could rotate my head. I could identify that there kind of looks like there's a triangle right here. Maybe I could figure out the components of that triangle and figure out theta, which is essentially what you are doing when you're doing the dot product. In this case, the product here looks like it is 2 plus 6 equals 8. But the dot product also equals the magnitude of r, the magnitude of s, times cosine of theta. So that looks like it is r, let's see, 1 plus 4, or 1 plus 9 rather, that's square root of 10, times square root of 2 times 2, times cosine of theta. And you could simplify that algebraically, but who cares? So then cosine of theta is 8 divided by what looks like to be root 20 over 2. That's just a number on the right-hand side. Then I plug that into my calculator to get that theta is about 26.6 degrees. Which is nice. It's a very straightforward way for me to find the angles between two arbitrary vectors. They don't even have to be in the first quadrant. One could be pointing, down here, for example, and I could find the angle just by using the dot product. So, dot product, very useful. Geometrically, think that if I have two vectors, let me call it f and r, perhaps. Right, this is giving me the part of f along r multiplied by the magnitude of r. Why I randomly chose f and r might become apparent soon. So this section of the course is talking about energy. We really didn't define energy yet in a very specific way, but other than that, it is some quantity that is used to represent motion, how much motion there is. And you might think, well, we already have something, we call it velocity. And you're right. Velocity is describing very specifically the motion. But I think we would agree there's something different about, say, a semi-truck careening down the street at 100 miles per hour versus a skateboarder careening down the street at 100 miles per hour. If either of those were to unfortunately collide with, say, a wall, there would be very different outcomes for the wall. In the case of the semi-truck, goodbye wall. In the case of the skateboarder, goodbye skateboarder. So you might think that there's something also, if I want to describe motion in a way that might have something to do with the mass of the object. Larger objects that are in motion, I'd rather have a mosquito flying at me, at 50 miles per hour than I would rather have a baseball flying at my face at 50 miles per hour. They have the same velocity, but I think we can agree the baseball is going to hurt a lot more than the mosquito. And we saw this with Newton's laws of inertia as well, right? More massive objects have a harder time to get moving. You have to do more to get a more massive object moving. It's F equals ma. The same force applied to two different objects with different masses that same force gets the less massive object moving more or quicker, in that the acceleration is higher compared to an object with larger mass. You should be able to just look at Newton's laws and kind of qualitatively justify that statement with math. If you want to use numbers, you can use numbers, but just looking at the symbols, you should be able to see bigger masses result in lower accelerations for the same force. We also know that this motion can change through forces. Things can speed up, things can slow down, things can even change direction. Though in the case where they change direction, their speed is not changing, but the direction is changing. Forces were involved in talking about how the direction of objects change. Is it moving west, east, up, down, in a circle? We had to look at forces that were working immediately on the object to change its direction, speed it up or slow down. There are two different ways I can approach this. I can first define work, and that leads towards this thing called kinetic energy. Or I can start with kinetic energy, and we can see that the way that kinetic energy changes is because of this thing called work, which has to do, intuitively, with forces. I'm going to take the latter approach, and I might actually do the other approach. Maybe that's an optional thing at the end of one lecture. So we're going to define kinetic energy as the energy associated with motion. If an object is moving, i.e. its velocity is non-zero, it has energy. It can be quantified by the following formula. Actually, I should check, see what your book uses. I think it uses K. Yes, it uses K. So I will use K. We can define the kinetic energy K as 1/2 the mass of the object times the square of the magnitude of the velocity. You might hear this colloquially just said as 1/2 mv squared. But I want to be more specific and again bring to the front the point that it is the magnitude of the velocity that matters here. Another way you might see this written, given we just talked about the dot product, is that the kinetic energy is 1/2 the dot product of velocity with itself. And that is, again, of course, just the magnitude squared. Note this is a scalar. 1/2 is a number, mass is a number, the magnitude of the velocity is just a number. There's no directionality associated with this, not a vector. It required us to know about a particular vector, the velocity vector, but it says nothing about the direction that the object is moving in. An object that's moving 30 miles per hour east and an object that's the same object moving 30 miles per hour north both have the same kinetic energy, even though their velocity vectors point in different directions. The units of energy, so the units of K, is the unit of 1/2 mv squared. 1/2 doesn't have a unit, so it's the unit of mass times the unit of velocity squared. In MKS units, that's kilogram, meters per second all squared, or kilogram meters squared per second squared. Energy has become so fundamental that we give this thing its own name, similarly naming it after a physicist that studied energy in great detail. We call this the joule, or joules. It's just the joule. J, after James Joule. I guess I've closed the PowerPoint, but the sprightly individual with the big beard that was on my first slide. Let's see if I can bring him up real quick. Where are you, Joule? There you are. That guy. We can applaud his beard. We can also applaud all the work he did in thermodynamics, our study of energy, entropy, and whatnot. A lot of that is attributed to Joule. All right, so energy is measured in joules. So what is this equation saying? Which deserves a highlight, by the way. It says more massive objects that are moving at a given velocity carry more energy. A semi-truck moving at 30 miles per hour carries more energy with it than, say, a baseball moving at 30 miles per hour or a mosquito moving at 30 miles per hour. It scales quadratically with the velocity. Double the mass and you double the kinetic energy. Double the velocity, magnitude, and you quadruple the kinetic energy. A factor of 2 increase in velocity results in a factor of 4 increase in kinetic energy. So any motion can be associated. There can be a single quantity, which is, it's nice that it's not a vector. It's a quantity that just kind of, you just carry in your pocket along with you, like your mass. You know, it's just a number that you need if you ever need to do a calculation. You also have kinetic energy that is associated with your motion. Now we could ask, how do you get kinetic energy? Well, you start moving. Well, how do you start moving? Well, I had to accelerate. Well, how do you accelerate? Well, through forces. So now the question is that how do forces can cause objects to speed up, slow down, change direction. How do forces change kinetic energy? And what is relevant here, which might help motivate why the dot product is important, is we've talked before, again, you're probably so sick of hearing me give these examples of when objects speed up or slow down depends on how the velocity and acceleration are oriented with one another. A and V, this is an example of speeding up. V and A, this is an example of slowing down. In both of these cases, the magnitude of V changes. This is a case where they change direction. The magnitude of V does not change, which then implies kinetic energy does not change. Where above, this implies kinetic energy does change. Whether the length of the velocity vector got bigger or smaller depended on what forces were acting in the same direction as the velocity. I.e., there was a net acceleration in the same direction as the velocity, or there was a component of the acceleration in the same direction as the velocity. That component is what mattered. The dot product tells you, give me two vectors, the dot product tells you how much of, say, a vector f points in the same direction as your displacement or your velocity. The dot product is helpful here because it can tell us what part of the force is actually helping to speed up or slow down an object. And as what I'm motivating here, it's that component that changes kinetic energy, the part that's parallel or anti-parallel to your motion. So now let's think of this in terms of let me motivate this first before I get into the more hairy calculus. Suppose you start here. You start at this point. You go out in some direction R1. You end up at some new point. You then turn and move in some direction R2. I could draw that as a vector as well. You remember we add vectors by just putting base to tip. And then from there I go some other direction R3 and end up there. I could define my displacement in the usual way as my final minus my initial. That would be my displacement. But I got the displacement by doing the sum of all my individual little steps. I took one step R1. That's right, that should be an I. Which just means I'll just write it out so it's clear. R1 plus R2 plus R3 in this case. I started at my starting point. I went out R1, then I turned, then I went R2, then I went R3. I ended up at some final location. My total displacement resulted from the sum of each of my individual little treks. If instead I was measuring this in terms of time and velocity, we could say something very similar. I could erase these. Suppose I have some velocity vector that's pointing in a given direction. Oops, I erased the wrong ones. Sorry. Do a little swap. Suppose I have a velocity vector, and in each of these three increments, I cover each of those increments in the same amount of time, delta t. Right? I have some velocity vector times delta t here. I have some velocity vector times delta t here, and I have some velocity vector times delta t here. Again, my total displacement is the sum of my individual velocities times delta t. I add up each part of my path to get to my final location. Now suppose I do the same thing, but instead of 3 treks, I have maybe 47 billion little treks. Maybe my velocity direction is constantly changing, and I end up here. And each of these little individual pieces is its own velocity times some little delta t perhaps. But my displacement overall is when I just add them all up. My overall displacement is the sum of those individual velocities times delta t. You could imagine we could do even more. Instead of a billion, I do a billion billion. Or I shrink delta t so that all of this is happening. Every little leg of my journey, I'm doing it over an incredibly tiny, tiny, tiny amount of time. But now there are billions upon billions of these little individual steps. Recall that we said that we can write that down then as the integral of the velocity over time. Again, the integral is just a fancy word for add up all the things. I'm adding up each little v times dt, and then there might be billions and billions or infinite number of them. I add them all up, and that gives me my total overall displacement. Another way we could have arrived at this is just to recall the derivative definitions. This was the definition of velocity, your change in position over time. The derivative is just a fancy word for slope, rise over run, how the position is changing divided by how much time is elapsing. So I could, of course, write that as that is the same thing as this. this might be referred to as a differential expression, where this is saying each tiny, tiny, tiny change in R is a result of velocity times time. And if my velocity is changing, that should be also cover the v as well. And if velocity is changing, then I just take that into account as I calculate my overall change. So this differential form is telling you each tiny little change in your position, the left-hand side, is equal to whatever your velocity is at that moment times a little bit of dt, a little bit of time. You can turn this into an integral expression just by throwing down integrals on both sides. That is the same thing. Now I'm just doing the integral version. This might be called an integral expression. And usually with integral expressions, we can't actually evaluate everything. You know, notice this, we can't evaluate, but this we can. The integral means add up all the tiny little things. There's a bunch of tiny little changes. That is just nothing more than your overall displacement. So again, this is just all this is saying is your overall displacement is the integral of v dt. And how I arrived at that through these calculus expressions. Because again, you might be wondering, who cares? Here's why you should care. Now let's actually look at kinetic energy. It is 1/2 mv squared, which I'm going to write as 1/2 mv dot v. And now we're going to ask, how does kinetic energy change? Change is a word for the derivative, or rather derivative is a fancy word for change. So what I'm asking here, I could actually be more specific. How does kinetic energy change with time? So in that case, all I'm asking is, what is dk over dt? I guess I've been writing ke. What is dke over dt? Or what is the derivative with respect to time of kinetic energy? How does something change with time? You're asking about what its derivative is. How does position change with time? Velocity. How does velocity change with time? Acceleration. Now I'm asking, how does kinetic energy change with time? Well, we are more than capable of taking a derivative. I'm going to go back to just k, sorry. So that is then the derivative of our expression for kinetic energy. If the mass is a constant, so the mass is not changing, then constants come out of derivatives. That is just 1/2 times the derivative of the dot product. We saw above that the dot product has a product rule. So this is the same thing as dv dt dot v plus v dot dv dt. That should look familiar. That is nothing more than just the acceleration a. Also remember that that the dot product also is commutative. So these two terms are actually the same. A dot v is the same thing as v dot a. So then I would say that's 1/2 m, and then it's 2 v dot a. because both of those terms are the same, there's a 2. The 2 cancels with a half. We've then written down that dk dt equals m v dot a. Or I could write this as v dot m times a. We know what that is. V dot f. Which this is called power. So how does kinetic energy change with time? It is the velocity of the object dotted with the force that is acting upon it. Forces can change kinetic energy, but not just any force acting on an object. The force has to be, you take the dot product with v. So again, we could interpret this geometrically. Remember, this takes the magnitude of v and multiplies it by f cosine of theta, where theta is the angle between v and f. Or said another way, only the part of f along, which by that I mean parallel or anti-parallel, v changes kinetic energy. Do I want kinetic energy to change? I need to apply forces. Any force in any direction? No. The force actually has to be pointing in the direction of motion or directing anti-parallel to the direction of motion. Just like what we said, just like what we said here. When we said that things speed up or slow down only when the acceleration is parallel or anti-parallel to the velocity. That is the only way that the magnitude of v changes. That is the only way that kinetic energy can change. If they're perpendicular to one another, the magnitude does not change. And we did at the very beginning, we talked about how when two vectors are perpendicular to one another, the dot product is 0. So in that case, then, this dot product, v dot f, would be 0 if the force was perpendicular to velocity. Forces along the direction of motion change the kinetic energy. The units of power, by the way, are energy per time, which also comes up so much, it's given its own unit, which you have definitely heard of, called the watt. I should be more specific. In MKS units, that is then the joule per second. The joule per second is called a watt. A 30 watt light bulb is saying that 30 joules of energy are being converted to light every second. Which actually is wrong, because a lot of it goes into heat, which is why these LED lights for the same wattage appear much brighter, because less of it is going into heat, more of it goes into light, but your light bulb is using a certain amount of energy. Nowadays with the LED lights, more of it can be turned into light. Or to get the same brightness as the bulb as it was before, you need overall less energy because you're not losing as much to heat. All right, so we wrote dk dt equals v dot f. Our takeaways there were that forces along the direction of motion v or anti-parallel to the direction of v, those are the only forces that change kinetic energy. I'm going to write this a different way. I'm just going to move the, well, first I'm going to flip the f and the v. And then I'm going to move the dt to the other side. This is saying the change in kinetic energy is a force dotted with v dot, or v dt. Because remember, dt is just a number. I can put it anywhere in the dot product. But v dt, man, it's as if I planned this. Did I not write down somewhere here? Ah, right there. That v dt is just the change in displacement. So now I can write down the expression here. I can write, not as a highlighter, I can write dk, the change in kinetic energy, equals force dotted with displacement. Again, let's interpret this as a sentence. Changes in kinetic energy are because of forces acting in the direction, which means parallel or antiparallel, of the displacement. And sometimes I like, if I think of this as this, I wrote it down as an equation, then I wrote it down in words. This dk is this part. The equal sign is this part. And then the right-hand side is this part. Changes in kinetic energy are because of forces acting in the direction of the displacement. Why is that the case for the right-hand side? Because of the dot product. The dot product takes the component of f that points in the same direction as your displacement. So anything that's perpendicular gets thrown away. I could write, usually it's written like this, f dot dr. This right-hand side is called work. In physics, the term work is used to describe the component of the force over a distance. You might have heard it explained as forces that are acting on an object over a distance are that is the physics definition of work. The cutesy examples, I can hold this apple up. I'm exerting a force on this apple, but the apple is not moving. So the force I'm exerting on the apple, which is pointing upwards, is not in the same direction as motion. In fact, there is no motion. So my hand is not doing any work on the apple. I could go up to the wall, and I could push on the wall with all of my might until I crumble into a blob of exhausted mass. The wall does not budge at all. I'm not really budging at all as I push on the wall. I am doing no work on the wall. Which you might think, what do you mean? You're going to clearly get exhausted. Yes, but that's another example of how the word in physics does not match the common, I almost said the common tongue. This is not D&D. The common use of, now I can't think of anything else, the common use of the word work in everyday language. Work requires forces that are acting over distances. If this differential thing scares you, that is the exact calculus way to think about it. the approximate way to think about it, it might be easier if you think of this as a big delta. You know, the change, well, in this case, really, we just call it, we would just probably call it work. Right, the work that's being done is the force that's being applied over some amount of distance. So then the expression I wrote above, if you wanted to think of the approximate version, you could say the change in kinetic energy is equal to the work, which is the force over some amount of distance. And that actually is not too bad. For more general problems, the way you would solve this is using integrals, but for the questions in this class, we'll never, I don't think we'll really have to ever use a hardcore integral, but I wanted to write down the exact version of this. Because, how much room do I have? Not enough. We can now write down, I could be so bold as to say the fundamental theorem of energy, or the expression, the energy expression that is all you really need to know to understand energy. I'm rewriting that just to get rid of all the colorful highlighting. So again, this expression is saying that the kinetic energy changes because of work being done on the object. Right. I do a little amount of work, dW, and the d just means a tiny little bit of. I do a tiny little bit of work by exerting a force over a tiny little bit of displacement or distance. That changes my kinetic energy by some little bit. And I could ask, what is the total change in kinetic energy between 2 points? And these 2 points might be widely separated in position. You know, I'm not just talking about t equals 0 and then t equals 1 picosecond. You know, I might be talking about, you know, a starting point over here and an end point that's across the room. If I'm applying a force the entire time, I might be interested to know how does the velocity or the kinetic energy overall change. Well, I have all these tiny little increments of work. I'm doing a little bit of work, each little displacement that occurs as you move across the room. So how do I add them all up? Well, that, of course, is the integral. The integral is a fancy word for add up all the things. So then the integral of the change in kinetic energy is then just the integral of work, where you have some k initial and some k final might be your limits. Here this might be some initial position, and this is your final position. And you could go back to the crib sheet handout or the lecture if this is still a little foreign to you. The left-hand side is actually pretty easy to write down. Again, the change, all I'm asking is what is the overall change in kinetic energy, right? That, or kinetic energy final minus kinetic energy initial. And that is equal to this integral of force over displacement. I add up all the forces that are acting in the direction of motion, all those little bits of work. And then if I get that, that tells me exactly how my kinetic energy changes. The kinetic energy changes because of the total work being done on the object. This definitely deserves a highlight. So So this is called the work-energy theorem. How does my kinetic energy change? Let me calculate all the work that's being done on me, and I'll tell you. Work changes kinetic energy. If I add up all of those changes, I get the total change. And I'll just say for multiple forces, if you have multiple forces, nothing really changes. Remember, Newton's laws talked about the net force, where you were doing the sum of the vector forces. Same thing here. I could just write that the total change in kinetic energy equals the integral of F net instead, dotted with dr. This right-hand side might be written as your net work that's being done. So that might be the more general direct version of the work-energy theorem. Conceptually, this is huge. It's very important because what this is saying, it's saying how forces transfer or create or do something with regards to energy. This is how forces get turned into motion. Just by exerting a force on an object does not guarantee that it's going to move. I have to exert the force in the direction of the motion in that case. In that case, then me smacking the apple, that occurred over a displacement. The apple was in contact with my hand for a while, though you couldn't see it because I slapped it pretty quickly. But if we did that in slow-mo, there would have been a good amount of time where I was moving the apple with my hand and therefore exerted a force on the apple. That slap, which was in the same direction that the apple was moving, is what gave the apple a kinetic energy. It's what gave the apple a speed. As opposed to my other hand, which was just holding the apple. So let's make sure I did not forget anything that I wanted to describe on this before I do a few examples. Yep, I think we're good. All right, simple example 1. You have a box that is 2 kilograms. You apply a force horizontally, F, that is a constant force. Let's see, let me give it a number. Let's say F is 10 newtons horizontal. Then I could say, what question can I ask? Well, I guess we could solve this in 2 different ways. Let's actually do that. After 2 seconds, what is V? Let's assume the box starts at rest. In this case, the free body diagram for the box might look something like this, with gravity, the surface of the floor, and then the push. The vertical forces balance each other, which is why the box doesn't start to float or sink. And then the force of the push is what makes it start to accelerate to the right. I think it's obvious that the displacement that occurs is going to also be to the right. In this case, the force is going in the same direction as the displacement. That will be important. Now I could solve this with Newton's laws. I could say, okay, by Newton's law, F equals ma. The acceleration is then F divided by m, which is in this case 5 meters per second squared to the right. That is a constant. So I could say, okay, the displacement then, delta x, is v naught t plus 1/2 a t squared. It started at rest, so this part's gone. A is 5, t is 10. I plug that in. Oh, sorry, t is 2. T is 2. So a is 5, t is 2. 2 squared is 4, divided by 2 is 2, times 5 is 10. This equals 10 meters. The velocity, the final velocity, is the initial velocity times at. That is then 10 meters per second. Okay. Now I could do this using work energy. Work energy says that the change in kinetic energy, or kinetic energy final minus kinetic energy initial, is equal to essentially the total, the net work being done on the object, or the net, forces in the direction of motion. The integral might seem scary, but if it's a constant force, that is the same thing as just that constant force times the overall displacement. You go back above where I did the integral of displacement was the integral of the triangle r, capital delta r, is the integral of all the tiny little displacements. And the force, being a constant, can come out of the integral in this case, which is where this comes from. So tell me the force that's acting on across a given displacement. This, of course, is just the magnitude of the force times the magnitude of the displacement times cosine of theta. But they're acting in the same direction. The force and the displacement both are horizontally to the right. The angle between the two, if I were to draw them, here's r, and then here's f. The angle between the two are 0. So cosine of 0 is just 1. This is just the magnitude of the force times the total displacement. But we just calculated, we said this is 10 newtons. And the total displacement in this case, we found from the previous problem, was 10 meters. You could figure out the units, and you should find that a Newton meter is indeed a joule. It's the same units as joules. So this tells me that the kinetic energy has grown by 100 joules. So delta K, or delta KE, is KE final minus KE initial. That's just the definition of the deltas that we've seen before. So the final kinetic energy is the final velocity, involves the final velocity. Then the initial kinetic energy involved the initial velocity, and that must equal 100 joules. If the initial velocity was 0, this is gone. You can then solve for the final velocity, and you will indeed get the same answer. Essentially 200 divided by 5. Do you get the same answer? You better get the same answer. What did I do wrong? Oh, wait. Sorry. 5 is the acceleration. The mass is 2. So yes, the mass and the 1/2 cancel each other out. V squared is 100. Square root of 100 is 10. The final velocity is 10 meters per second. Phew. Okay, good. I'm so excited. You get the same answer through both methods. Both methods help you arrive at the exact same result, as must be the case. Do not think that energy and forces are completely disparate, unrelated. This also shows that this is an example where sometimes you can solve a problem in two different ways. Sometimes one way is much easier than the other way. And for every single problem in this class, we could do Newton's laws to solve the problems. But we will find that there is going to be incredibly more complicated problems in this class, where we can do it in 2 lines if we use energy. Else it would take us 2 pages if we were to use Newton's laws. Okay, right at an hour. So let me just do the same problem, but now I push down at a 30-degree angle. So this is 30 degrees. Again, 2 kilograms. 10 newtons of force. But now it's at an angle. Now the force vector in this case is not just 10, 0, but it's 10 cosine 30 newtons, and then negative 10 sine of 30 degrees newtons. The displacement is still only horizontal. Delta R in this case is some number multiplied maybe by I if we wanted to use the IJK notation. It's only moving in the horizontal direction if I want to write it down as a vector. Actually, I can be more specific. Instead of a question mark, I can write it down as whatever this displacement is. I just don't know it yet. It has some magnitude. But therefore, the dot product between these two is just, if I do the product of the first two, I get 10 cosine 30 degrees delta R plus negative 10 sine 30, but multiplied by 0. So then the overall is just the first term. Could have also thought of this as if F is 10 newtons, right? F times delta R is the same thing as the magnitude of F, which is 10, the magnitude of the displacement, which is that delta R, times the cosine of the angle between them. But that angle is just 30 degrees. So again, this gets you 10 newtons times delta R times cosine of 30 degrees. You get the same answer. Cosine of 30 degrees is positive. This entire thing is positive. This is the work, the delta work that's being done. And it's a positive number. We will see positive work increases kinetic energy. Negative work decreases kinetic energy. And why? Well, simply because of the work-energy theorem. Because we can then take this and write it down in the expression we had above and say that the change in kinetic energy, which is final minus initial, but the initial is 0, so I can just write it as final minus 0, equals the total work that's being done, which in this case, a constant force acting over a distance. We wrote that this is 10 newtons, or rather, I'll put the unit at the end. This is 10 cosine 30, delta R. Yes, there's a 10 newtons, but then it's multiplied by delta R that gives you joules. Now, if I tell you that you again move the box 10 meters, like what we did above. Here we said after 2 seconds the box moved 10 meters. Suppose now in this case I do it again and I move it 10 meters in the horizontal direction. This delta R then just becomes 10 meters. But in this case, you don't get 100 joules, you get something that's 50 times the square root of 3 joules, which is less than 100. Why? Because now not all of your force is in the same direction as motion. Some of your force is pushing down on the box. Not all of your force is pushing in the same direction the box is moving. So then you would find as a result the final velocity is 9.31 meters per second instead of 10 meters per second. You covered the same distance, but since you're pressing down on the box and not horizontally with the box in the direction it's moving, the final velocity that you get is not as high. Again, the whole idea is that the acceleration vector is, what's speeding up the velocity is the part of the acceleration that's pointing in the same direction as the velocity. In this case, with the net force pointing at an angle, not all of that turns into an acceleration along the direction of motion. All right. More work energy next time, and then we will start looking at specific forces, particularly gravity and the spring. And then we'll start to look at properties of kind of how those forces cause energy to change. But again, overall, that is all you really need to know about energy. Work changes kinetic energy. If you do positive work, so the right-hand side is positive, that makes delta kinetic energy positive. Your kinetic energy increases. If a force does negative work, then that means that the kinetic energy decreases. So again, an idea is, I throw an apple into the air. This is the next lecture, admittedly. I throw an apple into the air. There's a part where the apple slows down, comes to rest. During that upward motion, the direction the apple is moving up that entire time. But the force of velocity is pointing down. We will calculate next time that for that part of the journey, gravity is doing negative work, and as a result, the kinetic energy decreases. Then when the apple turns around, it is moving in the same direction as gravity is pointing. Gravity then does positive work, and the apple speeds up.